Hello everyone. Here we are with another chapter of your book. It's chapter 31, I think, and it's a continuation of the chapters on threads. And this time we are going to study another structure which is called semaphore. So far we have studied two structures that we can use for synchronization between threads. Number one was locks, which we said they could be used for implementing mutual exclusion between threads. And secondly, we have studied condition variables, where they can be used for making your threads wait until a certain condition is fulfilled. Okay, so this time we are going to study semaphores. Semaphore is another abstraction which was invented by Dijkstra. You must have heard Dijkstra's name in your data structures course because he is very famous for that shortest path algorithm. Okay? So it's the same Dijkstra who has invented these semaphores, which can be used for synchronization between threads. The good thing or the good property of semaphores is that they can be used either as locks or as condition variables, okay, depending on how we want to use them. Semaphore can perform the role of both locks as well as condition variables. So semaphore again is an abstraction which is a data structure provided by a library or operating system, and there are two operations defined on semaphores. One is semWait and the other is semPost. Okay, so semaphores are, as I said, data structures. You can define variables of type semaphores, and on those variables you can perform these two operations called semWait and semPost. So what are these two operations and how do they behave? Let's see. So semWait and semPost, they both take a pointer to a semaphore or the address of a semaphore. And the behavior of these two functions is that internally semaphore maintains a value. Okay? So what semWait does is that when you pass it a pointer or address of a semaphore, it will decrement the value of the semaphore, okay, whose address you have passed. Let's call it S. So it will decrement the value of the semaphore S by 1 and wait if the value of semaphore S is negative. Okay, so initially the semaphore will have some value. Usually it is a positive value. It will decrement that value. Okay, so semWait will decrement that value and see decrement it by 1 and see if the value has become negative or not. Okay, so if the value has become negative, then it will put that thread to sleep and wait. Okay. So I'll repeat. semWait, it receives a semaphore, the address of a semaphore, and what it does is it will decrement the value of that semaphore by 1, and if the value become negatives, it will put that thread to sleep. The calling thread, which called this semWait function, it will put that thread to sleep if the value after decrementing becomes negative, and the thread will wait for some signal. Okay? So it will wait until some other thread calls semPost on this same semaphore. Okay? So semPost again is a function that takes a pointer to a semaphore or the address of a semaphore, and what it does is it increments the value of the semaphore by 1. Okay, it's the opposite or complementary of semWait. semWait decrements the value and semPost increments the value. Okay, and after incrementing the value, semPost will check, are there any threads waiting for this semaphore? Just like condition variables, semaphores also internally they maintain a queue, and any threads waiting for that particular semaphore are waiting on its queue. So semPost, it will increment the value of the semaphore by 1 and see, are there any threads waiting on the queue of the semaphore? If there are, it will wake one of them. Okay, so just like condition variables, it will see if there are any threads waiting on the queue of the semaphore, and if there are, it will wake one of them. Okay, and all this will happen after it has incremented the value of the semaphore by 1. So I'll repeat again, semWait it will increment, some wait will decrement the value of semaphore by 1, and if the value becomes negative, it will put the calling thread to sleep and put it on the queue of the semaphore. Some other thread ultimately will call sempost. Sempost will increment the value of the semaphore by 1 and see if there are any threads waiting on this on the queue of this semaphore, and if there are, it will wake one of those threads. So pthread also provides you with this semaphore library, and it provides you with this semaphore.h file, which provides you this type sem_t. So this is a type for semaphores. You can declare variables of this type, and on these type of variables sem_t type, you can call these functions semWait and semPost. Okay? So semWait_t, you declare a variable of this type, let's say call it s, and initially you initialize this semaphore. Okay? So seminit, it takes the address of a semaphore and the initial value that you want to give to this semaphore. Okay, so this third value is the initial value that you want to give to this semaphore. Remember, in these functions, we discussed that internally semaphore maintains a value, and semWait and semPost, they will decrement or increment that value of the semaphore respectively. So what's the initial value that we give to the semaphore, or what is the initial value that the semaphore will have? We define it here by calling seminit. This third argument, we can give it any value that we want to give to that semaphore initially. Okay, so here it is initializing this semaphore s with the initial value of 1. The second argument is 0 or 1 depending on whether this semaphore will be shared between threads of the same program or between different programs. Okay? So 0 means it will be shared between threads of the same program. Okay? So this is a scenario that we are going to consider. So these are the arguments of the function sem_init. So you can define these variables as of type semaphore of this type sem_t, and you can initialize them to any initial value that you want to give them. So let us see the use of semaphore, how semaphores are used practically. So let's say you have declared this semaphore of type sem_t, a variable of this type, and we call it m. Initially, we initialize the semaphore to some value. We'll see what is this value x. But let's say in the beginning we said that semaphore, we can use it as a lock as well as a condition variable. So let's say we want to use a semaphore as a lock. Okay? So to use a semaphore as a lock, what initial value shall we give to this semaphore so that calling these functions sem_wait and sem_post on this semaphore, they will behave as the function of the lock. Remember, we have to acquire a lock and release a lock. So sem_wait should behave like acquire a lock, and sem_post should behave as releasing a lock. Okay. So remember, if you remember the behavior of the acquire and release. So acquiring a lock, basically, when you call acquire function on a lock, it returns immediately if no other thread is holding a lock. And if another thread is holding a lock, this lock, then calling acquire function on such lock which is already being held by another thread, calling acquire on that lock will block our thread. Okay, so acquire function will block until the other thread releases the lock, and only then our thread will acquire the lock and will return. Acquire function will return. Okay, so keeping in mind the behavior of sem_wait and post like this, sem_wait, it will decrement the value, and if the value becomes negative, it will block. And sem_post will increment the value, and if there are any threads waiting on that queue, semaphore's queue, it will wake one of those threads. So if wait and post behave like this, then what value shall I give to X so that this semaphore M, it behaves like a lock, okay? And wait, sem_wait and sem_post behave like lock acquire and lock release. So what should be initial value of X so that if there is no other thread holding the semaphore, then sem_wait should return immediately. And if another thread has already called sem_wait on this semaphore and is in the critical section, then if we call sem_wait again, this sem_wait should block, okay, and not return until the other thread calls sem_post on this semaphore. Okay. So what should be this value of X? Pause this video and think about it like for 3, 4, 5 minutes to see if you can get to the point where you can guess this initial value. What value should we give here so that sem_wait and sem_post should behave like lock acquire and lock release for this semaphore M. I'll give you a few minutes. Pause the video. Okay, so if you have done some little thinking, you will have come to the conclusion that if we give an initial value of 1 to this semaphore, then this semaphore will behave as a lock. Okay? Let's run a scenario. We initialize this semaphore M to the initial value of 1. Okay, so replace X with 1. Now imagine there are multiple threads running, and they are before entering critical section, these multiple threads, they call sem_wait to acquire this lock semaphore, and once they have done with the critical section, they release this lock semaphore by calling sem_post. So if you have initialized this semaphore as 1, then the first thread that calls sem_wait, basically it will decrement the value in 1, and since the value is non-negative, value will become 0. This sem_wait function will return and this thread will enter its critical section. Okay. So while this thread is in critical section, the value of the semaphore has now become 0. And if another thread calls sem_wait on this same semaphore, what will happen is sem_wait will decrement the value of the semaphore. And now since the initial value was 0, then after decrementing, the value will become negative, -1. Okay. And if you see the behavior of sem_wait here, if the value becomes negative, then this thread blocks and goes into a wait. Okay. So this thread will, the second thread calling sem_wait will block because the value of semaphore has become negative. So the second thread will block. Okay. Now the first thread, ultimately it will basically finish its critical section and call sem_post on this thread M. Now see the behavior of sem_post. Sem_post increments the value of the semaphore. So the value of the semaphore now will become 0 again. It had become -1 when second thread had called the sem_wait. So the first thread after finishing critical section will call sem_post, and sem_post will increment the value of the semaphore by 1. So the value of semaphore will become 0. Okay. And then the sem_post function, it will see if are there any threads waiting for this semaphore. Yes, there is the second thread which had blocked while calling sem_wait. It is waiting for this thread. So this thread, the first thread, sem_post function, it will basically wake that second thread and return. Okay. So the second thread which had blocked in sem_wait, it will basically wake and return from sem_wait, and it will ultimately access the critical section. So in this way, I hope it's clear that if we initialize a semaphore to 1, then that semaphore gives us the behavior of a lock. Okay. So this is how semaphores can be used to imitate the behavior of locks. So here this is the same example. The first thread basically acquires the lock, calling sem_wait, value will become 0. And when the second thread calls sem_wait while the first thread is in its critical section, the value of the semaphore becomes negative, and the second thread will block until the first thread calls sempost value will become 0 and it will wake the second thread. So the second thread, now it will return from semwait and enter into its critical section. So at any given time, only one thread can enter a critical section. Thus, the semaphore gives us the behavior of a lock. It's called a binary semaphore because it oscillates between, it behaves like a lock, so it oscillates between values 0 and 1, or negative values and positive values. So now how can we use a semaphore to imitate the behavior of a condition variable? Okay. Remember the condition variables? We can call wait and signal on condition variables. When you want to wait for some condition, a thread will call wait on condition variable and it will go to sleep. And some other thread, after fulfilling that condition, will call signal on that condition variable, and the waiting thread will wake and start running. Okay. So the first thread waited until that condition was fulfilled, and only after the condition was fulfilled, it woke up and continued its execution. So how can we reproduce the behavior of condition variable using semaphores? So again here, let's say we use the same example that we used in the last chapter, that there is a main thread which creates a child thread. Main thread creates this child thread. This here it is, the code of child thread. And after creating the child thread, now main thread wants to wait until the end of child thread before printing this statement. Okay. So how can main thread wait for the child thread so that it can move further only after the child thread has finished? So here we create a semaphore, and in the main thread we initialize the semaphore to some initial value x, and as you can guess, again you have to guess the initial value of x so that the semaphore now behaves like a condition variable. So before I let you guess, let us see what happens here. The main thread will initialize the semaphore, it will create the child thread, and then it will call semwait on this S semaphore. Okay. So here we want the main thread to, if the child has not finished, we want the main thread to sleep and wait until the end of the child thread. Okay. So ideally, if the child thread has not finished yet, main thread shall go to sleep, and child thread, since it has been created, ultimately it will run, it will do its stuff that it's supposed to do, and after it has finished its task, just before returning, it will call sempost on this semaphore to signal the main thread that now I am finished and now you can wake and start running, and then it will return, child thread will end. So what initial value shall we give to this semaphore so that if the child has not finished and main thread calls semwait, then main thread should go to sleep, okay, until the child thread calls sempost. And if the child thread by any chance ran first and the main thread ran later and called semwait after the child thread has already finished, in that case semwait should return immediately and main thread should continue its execution. So what shall be this initial value of x? So pause this video and think about it for a couple of minutes and you will guess what's the value that we should give here to make this semaphore behave like a condition variable. So I'll give you a couple of minutes. Okay, so if you have thought about it, then I'm sure you would have guessed that if we give this semaphore an initial value of 0, then the semaphore will behave like a condition variable. Okay, so let's take both scenarios. Scenario 1, in which main runs first, initial semaphore value is 0 and main calls some wait on the semaphore. So some wait, as you know, will decrement the value will become negative, and some wait will put the calling thread to sleep. Child has been created, it will ultimately run, it will finish its task, and it will call sempost. Sempost will increment the value will become 0, and sempost will then see are there any threads waiting for this semaphore, and it will wait one of them. So main thread is waiting for this semaphore, and it will be woken, and it will continue return from some wait and continue its execution. So this is the first scenario. The second scenario is that after the creation of child, the child thread runs first. Okay, so child thread runs first, it does its stuff, and before returning it calls sempost. Since the initial value was 0, sempost will increment the value will become 1, positive 1, and sempost will see are there any threads waiting for this semaphore and try to wake them. Since main thread has not yet called semwait, it has not run, so there are no threads waiting for the semaphore, so sempost can't wake any of them, it will just return and child thread will finish. So child thread is finished, ultimately main thread will run and main thread will call semwait. Semwait will decrement the semaphore value. Remember, child had incremented the semaphore value and it had become 1. So main thread semwait will decrement the semaphore value. The value will become 0. And since it's not negative, semwait will return immediately and main will continue its execution. Okay, which is the correct behavior because main now does not need to wait since child threads had already finished. Okay. So giving an initial value of 0 to the semaphore makes it behave like a condition variable. So this is how we can implement the waiting condition using semaphores. Okay. So now in the last section, we also implemented this producer consumer problem using condition variables. The same thing can be implemented using semaphores. So we'll first try to build this producer consumer problem, implement it using some naive method using semaphores, and we'll see there are a couple of flaws which can be easily remedied. So here you have a buffer, an array in which producer will put values and consumer will consume values from this buffer. Okay. Buffer can have any size, call it max. So there are two variables which are like fill is telling you the next empty space in the buffer in which producer shall write a new value, and use is like the start of the values which have been produced but have not yet been consumed in the buffer. So the consumer will use this value to consume the next value which has been produced and not yet consumed in the buffer. So fill is basically where the producer will put the next value and then you increment fill to point to the next location, and it will ultimately wrap around after reaching the end of the buffer. Similarly, consumer will consume from this use location, and after consuming this value, it will move use to the next location, and use will also wrap around after reaching the end of the buffer. So this way, both producer and consumer, they'll produce and consume values from the buffer by calling this function put and get. So here it's a producer which is calling put repeatedly to put values in the buffer, and consumer calling get repeatedly to read values from the buffer. We are using two semaphores. If you remember, for producer consumer, we had concluded that we need to use two condition variables to correctly implement this problem. One on which the producer will wait and the other on which consumer will wait. Okay? And producer will signal the variable on which consumer is waiting, and consumer will signal the variable on which producer is waiting. So producer is waiting on this variable empty. Empty basically tells the producer that there is space in the buffer. Okay, so if there is space in the buffer, then producer will go ahead and put the value in the buffer and signal on the semaphore full, or this condition will full, so that the consumer should know now there are values inside the buffer and it can go ahead and consume them. Similarly, consumer will wait on this full variable so that it can be signaled by the producer that there are new values in the buffer. So it will wait until there are new values in the buffer, and once there are, it will go ahead, consume those values, and then signal on this variable empty to tell the producer, which is waiting for room to be created in the buffer, that now I have consumed the value and there is room in the buffer. You can go ahead and put new values. So producer who was waiting for the room to be produced in the buffer will go ahead and put new values in the buffer. So here, using this implementation, initially, let's say we uh, use this empty and full as condition variables. These are semaphores which can be used as condition variables. So what do you think of this implementation of producer and consumer? Since there are max position in the buffer, then here what we can do is that we can initialize the empty condition variable to max. Imagine max is 10, which means there are 10 spaces in the buffer. So we can initialize empty to 10 so that the consumer can call semwait 10 times and it will not, the producer can call semwait 10 times on empty and it will not block. Okay, so this way it will be able to put 10 values in the buffer, and after 10 calling semwait 10 times, this empty condition variable will become 0, and the next time the producer calls semwait on this condition variable, then it will block. Okay, which is the correct behavior, because after calling 10 times empty and putting 10 values in the buffer, now the buffer has filled, and since the buffer is filled, then producer should not produce any more values until there is more room in the buffer, and that will be when consumer has consumed some of these values and signaled this condition variable to tell the producer that now there is enough room. So think about it and see if there is any bug in this implementation. So take a couple of minutes, think about one producer and one consumer, different scenarios, and then take another couple of minutes or more and see if the same implementation, it works in the scenario where there are multiple producers and multiple consumers. So pause this video and think about this implementation for a few minutes. Okay, I hope you guys have thought about this implementation, and if you thought about it, then I'm sure you must have reached this conclusion that in the case of one producer and one consumer, this implementation works correctly. Okay, with whatever the size of max, this implementation works correctly in case of one producer and one consumer. But in case there are multiple producers and multiple consumers, then there's a problem. Okay? Let's see again, take the same example and imagine the max size is 10. Okay, so we have room for 10 values in the buffer. So what can happen is the function put, this is our critical section. Okay, so normally only one thread should be in the critical section at any given time. So if there were one producer and one consumer, then one producer at a time will be putting values in the buffer, so the mutual exclusion condition was fulfilled. But when there are multiple producers and max is, let's say, 10, then there can be a problem, because 10 means we can call semwait 10 times on empty and it will return immediately, and we can call function put. So let's say two threads, they call two or more threads, they call semwait on empty simultaneously. Okay? So both these threads, they will access empty one by one, and they both will decrement the value of empty, since in start value of empty is 10. So after decrementing by the first thread, the value will become 9. First thread will enter the critical section, and then after decrementing by second thread, the value will become 8. And again, since 8 is not negative, so second thread will also call put and enter critical section. Okay. Similarly, if there are more threads calling at the same time, then they will also enter critical section. This is a violation of the mutual exclusion principle. Okay. So there are many more than one threads. They are in the critical section and they are modifying this global variables simultaneously. So this is a race condition and it will corrupt our program, and the implementation therefore is not correct in case of multiple producers and multiple consumers. So how can we make this implementation correct even for multiple producers and multiple consumers? So again, the basic principle is that we have to somehow implement mutual exclusion when multiple producers access this thread or this critical section. So how can we do that? Again, for mutual exclusion, we need a lock. Okay, so we can put a lock in the program, and here it is, the implementation with the lock. So this is again a semaphore whose name is mutex. So we'll be using this semaphore variable as a lock. By initializing it to 1, we can use a semaphore as a lock. So we'll initialize this to 1, and whichever thread wants to call put, it should it shall first acquire this lock, and only then it can enter this critical section. Okay. So again, this same implementation is in producer, so therefore it will be in all producers, and same implementation is in consumer. Okay. So let's again take the scenario of multiple producers. So we will see here that if there are multiple producers, they call some weight on this mutex lock simultaneously. Then since the value is 1, initial value is 1, only for one of the threads, the sum weight will return immediately. Okay, it will reduce the value to 0 and return immediately, and that thread will enter the critical section. For all other threads that call sum weight will decrement the value will become negative, and all of those threads will go to sleep. Okay. So this ensures us that only one thread will be able to enter the critical section at any given time and call put. So here is an improved implementation of the again producer consumer problem for multiple producers and multiple consumers. But this implementation also has a small flaw. It has solved this problem where multiple producers were entering the critical section simultaneously by implementing mutual exclusion, but it has, this implementation, at least in this form, it contains another flaw. So again, take a couple of minutes and run different scenarios in which producer runs first or consumer run first, and see if there is a problem in this implementation. Take a couple of minutes and pause this video here. Okay, so if you have run different scenarios, then you might have reached this conclusion that there is a problem if the consumer thread runs first in this implementation. Okay, so initially the mutex value is 1. So what will happen is, and full is 0, empty is initialized to max, and full has been initialized to 0, and mutex has been initialized to 1. So if consumer thread runs first, then we'll see that it will call some weight on mutex. Since the initial value is 1, so it will be able to acquire the mutex. Some weight will return, and it will then call some weight on full, okay, to see if there are any values in the buffer. Since it's the first thread that the consumer has run and the producer has not run at all yet, so there will be no values in the buffer. And since full was initialized to 0, this sum weight, it will decrement the value of full to negative, and it will go to sleep. So this consumer thread, it will go to sleep while holding this mutex. Now, if any other mutex thread runs, again it will try to acquire the mutex and it will go to sleep also. If any producer thread now tries to run again to enter the critical action, it needs to acquire the mutex, and since mutex has already been held by this consumer thread which has gone to sleep, so it will not be able to acquire the mutex and it will go to sleep. So all producers and all consumers, they will go to sleep and there will be no thread running. Okay, so again, this is the flaw in this implementation of producer consumer. So this flaw where all threads get stuck and cannot move forward, no thread can progress and move forward, we call it a deadlock. Okay, so we'll study in the next chapter what exactly is a deadlock, but for the moment just keep this definition of deadlock, that deadlock is a situation where all threads, they are waiting for each other. Okay, they are waiting for each other in the sense that this consumer thread, it is waiting on full. Okay, and full, who is going to increment the value of full? It is this producer thread. Okay, so this consumer thread is essentially waiting for a producer thread on this variable condition variable full. And the producer variable, it will call Semaphores on full only after it has acquired the mutex. Okay? And who is holding the mutex? It is this consumer thread. Okay? So when producer thread calls Semwait on this mutex and goes to sleep, it is basically essentially waiting for this consumer thread to release this mutex. Okay? So the producer thread is waiting for the consumer thread and the consumer thread is waiting for the producer thread. So they both are waiting for each other and none of them can progress until the other has done some progress. So this is a circular wait, which in technical terms we call it a deadlock. It can be between two threads or more than two threads, but here in a very simple scenario we just discussed, it is between two threads who are waiting for each other and none of them can progress. So this is called a deadlock. So this uh, implementation has this flaw that it can cause a deadlock. So these are initial values of these variables. So how can we prevent this deadlock? We can prevent this deadlock if we can make sure in our implementation that a thread holding a mutex never goes to sleep. So if it has to go to sleep, then it should go to sleep before it acquires the mutex. Okay, so we should basically interchange these two lines. Okay, so it shall acquire the mutex after it has waken from sleep. Okay, so if it has to go to sleep, it should go to sleep without holding the mutex. Okay, so this mutex holding should be after this Semwait on full. Similarly, we should interchange these two lines also in producer. So here we have this new implementation where we are acquiring the mutex after we know that there is space in the buffer. Similarly, the consumer is holding the mutex after it knows that there are values in the buffer. Okay, so let's say if the buffer was empty, like we discussed the scenario on the last slide, consumer runs first, buffer was empty, and the consumer has to go to sleep on this variable full. Then in this implementation, we can see that it is going to sleep without holding the mutex. Okay, so in this way, the producer thread can acquire the mutex and put values in the buffer and then signal this consumer thread here to wake and consume them. Okay. So here you have a complete correct implementation of producer consumer problems using semaphores, which work for single producer, single consumers, as well as multiple producer, multiple consumers. So we basically have implemented all the things that we had implemented in the last two chapters, locks and using locks and condition variables. Here we have implemented all of them using semaphores. Now there is another topic, the locks that we had studied until now are very simple locks and they do not distinguish between any threads. So at any thread, any one thread can only access the critical section using the locks that we have studied so far. But there are a lot of problems where the access that threads make to the condition or shared variables is of two kinds. There are some threads who will be accessing the shared data for read-only purposes. And there are other threads who will be accessing the shared data in order to write or modify that shared data. Okay? So we can distinguish using the behavior of these threads. We can classify the threads into two types of threads. There are threads who want only read-only access to the data, and there are other threads who want write access to the data. Now the key insight here is that while those threads who want to write the global data, them we should prevent them from accessing uh, this data simultaneously, and we should implement or strictly implement mutual exclusion between these writer threads. But the other thread which only need read-only access to the data, we if we have if we can have an implementation where we can permit these read-only accesses to multiple threads so that they can access our data simultaneously, then there is no race condition between the threads which are only accessing the data in a read-only manner. Okay, so if you can allow multiple threads to access that data for read-only purposes, then we will increase our efficiency. Okay, because for read-only access, threads do not have to wait. Okay, so for efficient implementation, we shall allow read-only accesses to more than one threads. But if there is a thread which is modifying the global data, then we can't allow multiple threads to modify global data simultaneously. For that, we have to strictly implement mutual exclusion. Okay? So this kind of implementation of locks, which distinguish between reader threads and writer threads and allow multiple accesses to reader threads simultaneously, we call them reader-writer locks. So how can we allow multiple reads in parallel? So here's an implementation of a reader-writer lock, which can be simply like this. So you have this structure, which let's call it read-write lock, and it has a binary semaphore called lock, and it has a write lock, which basically only those threads who want to write to that data, they will be using this lock to implement mutual exclusion among themselves. And here we have an integer which will be basically keeping a record of the number of reader threads which are in critical section are accessing global data for read-only purposes concurrently at any particular moment. So this is a write lock which is used to protect the shared data or implement mutual exclusion on that shared global data. And this is the lock which is basically used to protect this structure. Okay, so that only any one thread can access this read-write lock structure at any given time. So we can initialize this read-write lock. Initially there are no readers, so this lock we initialize it to 1 so that only one thread can access this structure at any given time. And the read-write lock, which is basically the lock which will be protecting the shared data or shared global data among different threads, we also initialize it to 1 because these two semaphores, we want to use them as locks. So after initializing, here are the implementation. The threads that want write access to this lock, this global data, they will first have to acquire this read-write lock for write purposes. Okay. So here they will all the threads that want to have write access to shared global data, they will first have to call these functions, acquire this lock for write purposes. So they will have to call this rwlock underscore acquire underscore write lock on this lock before they enter the critical section. So it will basically internally call semwait on this write lock to acquire this write lock for any thread that wants to access shared global data for write purposes. Okay. So once a thread has acquired this lock, it will enter critical section and modify the data. Any other thread that wants to access the shared data for write purposes, it will also call this function and it will block. Okay, because semwait will decrement and the value of the semaphore will become negative and it will block. Similarly, for all the threads that call semwait on this write lock, while one thread is already in the critical section, they will also block. Until that thread that is in the critical section, it basically finishes its task and calls rwlock underscore release underscore write lock on this lock, and basically it will internally call sempost, and sempost will increment uh, the value of the semaphore and see if there are any threads waiting and wake one of those threads. Okay, so this is these functions will be called by threads which want write access to shared global data, and only one of them will be able to enter the critical section at any given time, thus guaranteeing mutual exclusion. Okay. For threads that want read access to the shared data, they will call these functions. So they will call rwlock underscore acquire underscore read lock. So read lock, basically what it will do is it will first acquire this lock so that it is the only thread that is modifying this structure. So it will increment the number of readers because it's getting a write access to, read access to the shared data. Initially, the number of readers is 0. So if the number of readers is equal to 1, after incrementing, if the number of readers becomes equal to 1, this means this particular thread is the first reader which is accessing this shared global data. So the first reader, before it accesses shared global data, it will also acquire the write lock. Okay? Because it will acquire the write lock because it does not want any other thread, write thread, to come and basically modify this shared data while it is reading the data. Okay? So the first thread will also acquire this write lock. So once the first reader thread, the first reader thread will also acquire this write lock, and when the first reader thread has acquired the write lock, this semwait will return and it will release this lock. So this lock, remember, it is used to protect this structure. So the first reader thread, it will return from this acquire read lock and it will enter the critical section. It will basically start reading that shared global data. While it is reading this shared global data, another thread, if it also wants to read the global data, it will also call this rwlock underscore acquire underscore read lock. So it will acquire this lock to access the structure. It will increment the number of readers, and now since the number of readers will become 2, it will skip this if statement and the if body and release this lock and return. Okay, the second thread, it will directly go and access shared data in critical section for read-only purposes. Similarly, all other readers thread, they will also call this function if they want to access shared data for read-only purposes, and they will increment a number of readers, skip this acquisition of write lock, and enter directly in the critical section. So multiple reader threads will enter the critical section and access this data for read-only purposes. Okay? So first reader only acquires this write lock, and while all these threads are reading the shared data, since they have acquired the write lock, the first reader had acquired the write lock. Meanwhile, while they are all reading the shared data, If any thread wants to write this shared data, it will call this function, it will try to acquire this write lock, and it will block. Why? Because the first thread is holding this write lock. So while they are reading this shared data, no write thread can access this shared data and modify it. So once they have all done their reading, after leaving the critical section, they will call this release read log. Okay? So all other readers will basically decrement the number of readers, and since the number of readers has not become 0, they will skip this same post and finish this function. Okay? So one by one, all those readers will decrement this number of readers and leave the critical section. The last reader which decrements this critical number of readers, it will make the number of readers equal to 0. Okay? So when the number of readers is equal to 0 and the last thread is also leaving the critical section, the last thread before leaving the critical section, it will call some post on this write lock to release this write lock. Okay? So that any thread that is waiting to access this write lock can now go ahead and acquire this write lock. Okay? So here we have basically an implementation of a lock which is called read line lock. It distinguishes between threads which want read access compared to threads which want write access to the shared data. If a thread wants write access to shared data, then it implements mutual exclusion and lets only one thread access the shared data for write purposes. But if there are threads that want read-only access to shared data, then this read lock implementation basically lets multiple threads access this shared data for read-only purposes. And since for read-only purposes there is no race condition, so it's fair to allow multiple reader threads to have simultaneous access to shared global data. So this is an implementation of read-write locks. Now we come to another classical problem between for synchronization, which is called dining philosopher problem. So it goes like this. There are n philosophers sitting on a round table, okay, a dining table, round dining table, and they have n forks between them. Okay, so there's a pair of fork between each. There's one fork between each pair of philosophers. A philosopher can only do two things, one at a time. Okay, it can either philosophize while it is he or she whatever is philosophizing, it has no needs of forks. Okay? So it can either philosophize or it can eat. Okay? To eat, the thing is, it needs both forks. It needs both forks left and right. Okay, so once it has acquired left and right fork, only then it can go ahead and eat. Okay? So as I said, it can do only one of those two things at a time. So here is a pictorial representation. We have these circles which are the philosophers. So n philosophers here on this table, we have 5 philosophers sitting on this table. And between them, they have 5 forks. Okay. So there is a fork between a pair of philosophers. Each two pair of philosophers have a fork between them. Now, imagine these philosophers, imagine they are acting independently of each other. They are either philosophizing or eating. Okay? So when a philosopher is philosophizing, it needs to do nothing. When it wants to eat, it has to get both forks, one to the left of it and one to the right of it. So only when it has acquired both forks, it can go ahead and eat. Okay? So now, as you can see, these forks are shared resources between these philosophers. Okay? So if we let these philosophers access these forks randomly without any synchronization, then as we'll see now, there can be a problem. So let's see what can be a problem. So let me go back to this previous slide. And here you have this philosophers threads. So philosophers are basically implemented, simulated as threads, and they are in a continuous while loop. They're either thinking or they are eating. But when they want to eat, they first have to get forks. So getting forks means they have to get forks, both forks, which are on one on their left and one on their right. Only once they have acquired both forks, only then they can go ahead and eat. Okay? So as you can see, or you can guess that in this function get forks, we have to implement this waiting condition that the philosopher has to wait until it has acquired both its left fork and right fork. Only then it can go ahead and eat. So we have to implement some waiting mechanism in this get fork function. Okay? So after eating, it will call put forks, which will basically release those forks. And once the one philosopher has acquired a fork, then another philosopher, if it wants to acquire the fork, then we should not let it acquire the fork. We should make it wait until the first philosopher releases the fork. Only then the second philosopher can go ahead and acquire the fork. Okay, so this kind of waiting mechanism we have to implement in this problem. So here is a pictorial representation that we saw, and we have to implement get forks and put forks such that there's no deadlock. Remember deadlock in which every thread is waiting for the other thread and there is no progress. They're all stuck. So our implementation should not have a deadlock. It should be a fair implementation in the sense that no philosopher should starve, and ultimately every philosopher should be able to acquire the forks and get to eat. And we should implement in such a manner that at any given moment, maximum number of philosophers possible can eat. Yeah. So here in the get forks function, we basically call these two functions left and right. Left basically gives you the left fork for a particular, we give it a number of philosopher, and left will give us the left fork of that philosopher, and the right will give us the right fork for that philosopher. So let's say take this philosopher P2. Okay. So left of P2 is this fork, which is F2. Okay. So left of 2 is 2, and right of 2 is this F3. So right of 2 will return us P plus 1 or 2 plus 1, 3. Okay. We are doing this modulo 5 because for philosopher number 4, its left fork is F4 and its right fork is F0. Okay. So left of 4 is 4 and right of 4 is 4 plus 1, 5, modulo 5, 0. Okay. So these two functions basically given a philosopher will return you their left and right fork. So if we have this information, then let us see how we can implement these get fork and put fork functions that we had here. Remember here in this example, each philosopher is first doing get forks to acquire both forks left and right before getting to eat. Okay. So before when acquiring these forks left and right, we have to make sure that both left and right forks were free. No other philosopher was using them. Only then we can acquire them and this function can return. Okay. Otherwise, if the fork was busy, either left or right, then this function should block and return only after it has acquired both the forks. So let's see. So we, since you have to implement this waiting for forks if they are busy, we basically associate a semaphore with each fork. Okay, so for each fork, we define a semaphore. We have 5 forks, so here we define 5 semaphores. we call them forks, and we initialize each of them to 1. Okay? So we initialize them to 1 because a fork can be acquired by only one philosopher. Okay, so one philosopher that acquires the fork, it will decrement the value of that fork to 0, and any other philosopher that want to acquire that fork will call some wait, and value will become negative, and it will wait until the previous philosopher releases the fork. Okay? So we initialize the semaphores to 1. So here basically is an implementation of get forks and put forks. So to get forks, we have to get the left fork and the right fork. Okay, so we call some weight on a semaphore associated with the left fork and some weight on the semaphore associated with the right fork. Okay, if both these forks are free, only then these two sum weight functions will return and our get forks function will return. Okay, so if both are free, then returning of this sum weight function for both forks will tell us that we have acquired both the forks, and get forks function will return, and we can go ahead and eat for that particular philosopher. If any of those forks were busy, then a sum weight function of any of the fork will block, and get forks will not return, and that philosopher will wait until some other thread that is holding the fork calls some post in their put fork and releases the fork. Only then we'll be able to acquire the fork, and this get forks function will return. Okay? So again, let me go back and show you this implementation. So after thinking, a philosopher will call get forks, and get forks will basically get the left and the right fork by calling some weight on both those semaphores. And once, if both the forks are free, only then some weight on those two semaphores will return, and get forks will return. Okay, and then we'll know that we have acquired both the forks. We can go ahead and eat for this particular philosopher. So if this is implementation of get forks, and once we have eaten, we will basically release the left and the right fork for this particular philosopher P by calling some post on the semaphores associated with their left and right forks. Okay, so we'll basically release the forks after eating. So if this is the implementation of get forks and put forks, and this implementation is being used by all the philosophers, which means all the philosopher threads have the same code. And this is the picture. Any philosopher that wants to eat will first have to acquire the left and the right fork. Is there any possibility of a deadlock in this implementation? See this implementation, go back to this picture, and basically think about it. Is there any possible scenario in which there is a deadlock in this implementation of the Danning philosopher's problem? So Danning philosopher's problem basically is a classic problem to illustrate the condition or like effects of a deadlock. So think about it for a few minutes, pause this video, think about it and see if you can find a scenario where there can be a deadlock. Basically, deadlock is caused by the scheduler. Think about this implementation, think about different scheduling scenarios, and see if the philosopher threads can be scheduled in such a manner that there's a deadlock, they all end up in a state in which they are waiting for each other, and no thread is able to progress. Take a few minutes. Pause this video. Okay. If you have thought about it, then you might basically come to a conclusion that there can be a scheduling by the operating system in such a way that, let's say, you have created this 5 philosopher threads. Okay? So they are scheduled in such a way that there's a deadlock. Let's see this scenario. This P0 philosopher thread, it runs first. Okay, so it runs first and it will call its thing. After thinking, it will call get forks function. Get forks function, as you can see, first calls some weight on the left fork and then some weight on the right fork. So let's see, P0, it runs first. After thinking, it calls get forks function. Get forks function called some weight on F0. It acquires F0, and before it can call some weight on the right function, right fork, it gets descheduled. Okay, so P0 is descheduled and it has acquired this semaphore for F0. Okay? And it has not yet called some weight on F1. So it gets descheduled and P1 gets scheduled. P1 gets scheduled, again it also calls get forks and it calls some weight on the left fork semaphore. It acquires it, and before it can call some weight on F2, it gets descheduled. Okay, so P1 gets descheduled while holding this lock on semaphore F1. Similar thing happens to P2. It gets scheduled, calls get fork, calls some weight on the left fork, acquires it, and before it can call some weight on the right one, this one, it gets descheduled. P3 gets scheduled, again calls get fork, calls some weight on the left one, acquires this before it can call some weight on the right, it gets descheduled. P4 gets scheduled, calls get forks, calls some weight on the left fork, acquires it, and then calls some weight on the right fork. The right fork, if you remember, has already been acquired by P0. So what it will do, some weight, it will block. Okay, so P4 will block in the same weight on the right fork. Now P0, which was descheduled, gets scheduled again. It calls some weight on its right fork. Remember, it had acquired the left fork, but before calling some weight on the right fork, it had got descheduled. So it calls some weight on its right fork, which is F1. And since F1 has already been acquired by P1, it will block also. It will block, P1 will get scheduled, and after it had called some weight on the left fork, now it will call some weight on the right fork, which has already been acquired by P2. So P1 will also block, waiting for F2. Same thing will happen to P2. It will call some weight on its right fork, which had been acquired by P3. So it will block on F3. Again, F3 will be scheduled, which will basically call some weight on its right fork, F4, which has already been acquired by P4. So P3 will also block. Okay. So again, P4 cannot run because it is already blocked, waiting for P0. Similarly, all these threads, they cannot run because P3 is waiting for P4, which is held by P4, and P4 is waiting for F0, which is being held by P0. P0 is waiting for F1, which is being held by P1, and P1 is waiting for F2, which is being held by P2. P2 is waiting for F3, which is being held by P3. Okay? So this way they are all waiting for each other, and none of them can progress because any progress will happen only if some thread calls put fork. Okay, after eating, they will call put fork, but no thread can call put fork because it cannot progress. It cannot execute further. It cannot return from get forks function. Okay, because they are waiting in a circular waiting for each other. Okay, so this is a classic deadlock situation. No thread can progress. Okay. So why is this happening and how we can avoid this deadlock? This is happening because all these philosopher threads, they are depending on each other. Okay, they are waiting for each other. There is circular dependency or circular wait which is happening. So we can resolve the situation if we are able to break this circular dependency. So how can we break this circular dependency? Basically, dependency is arising because all of these threads, they are acquiring the forks in the same order. First left, then right, first left, then right, first left, then right. So if we want to break this dependency, then we have to make at least one philosopher acquire the forks in a different order. Okay, so how we can do this? Simple. All the threads, philosophers, they acquire in the same order, first left, then right, except one philosopher, in this case p is equal to 4, which will acquire the forks in inverse order, first right and then left. Okay, so this way we will basically break the dependency. So if we go and see this situation, so acquires f0 and gets descheduled. P1 acquires f1 and gets descheduled. P2 acquires f2 and gets descheduled. P3 acquires f3 and gets descheduled. P4 will acquire forks in the reverse order. In the reverse order, how? It will basically, instead of acquiring f4, it will first acquire the right fork, which is f0. It will try to acquire this one, but since this is being held by p0, it will block. Okay? So it will block while f4 is free. Okay? So ultimately, p0 will be scheduled. It will try to acquire f1, which is being held by p1. So p0 will block. P1 will be scheduled. It will try to acquire f2, which is being held by p2. So p1 will block. P2 will be scheduled. It will try to acquire f3, which is being held by p3, and p2 will block. Okay? P3 will be scheduled. P3 will try to acquire f4. f4 is free because p4 did not acquire f4 first. It got blocked while acquiring the right fork. p4 is free. So p3 will be acquired to, will be able to acquire f4. It will basically acquire both left and the right fork, and its get forks function will return. Okay? So p3 will basically enter the eat function. It will eat and then it will put forks. When it will put forks, it will release both f4 as well as f3. When it will release f3, p2, which was waiting for f3, will be able to acquire f3. So p2 had already f2, now it has already got f3. So its get fork function will return, and it will eat and it will pose its put its fork. So it will release f3 as well as f2. f2 will be given to f1, which was waiting for it. So sorry, p1, and p1 will now have f2 and f1. So again, p1 will eat and put its fork. It will release f2 and f1, and basically ultimately f1 will be given to p0, which already had f0. So again, it will also return from get forks, eat and put forks. So it will release f1 as well as f0. p4 was waiting for f0. It will also basically get f0 and then acquire f1. So here we can see since there was no circular dependency, ultimately one thread at least got to make some progress and release the forks, and then all other threads got their turn. Okay, so this is was one way to break this circular dependency and have somewhat correct implementation of Dynamic Philosopher's problem. Okay, so this is the last topic in this book in which they tell you how you can implement semaphore using condition variables, okay, locks and condition variables. So again, inside of sem underscore t, they call their implementation sem underscore t, and it's a very simple implementation. Internally, it maintains a value and it has a condition variable as well as a lock. Okay? So initially, when you initialize semaphore, you give some value to it, and that value basically becomes the internal value of the semaphore, and we also initialize condition variable and the mutex. So when you call them it will basically acquire this lock. The lock is basically to protect this structure, and it will check the value of semaphore. If it is less than equal to 0, it will basically wait for this condition variable. Okay, wait so that some other thread basically signals this condition variable. Only then it will reduce this value and release the lock and return from some wait. And some post basically increments the value and signals this condition variable, so that if any thread is waiting for this condition variable, it will wait and return from this sem wait. Okay, so this is a very trivial implementation that they have done in this book. It's not as robust as the actual implementation that you would file in a library, but still it gives you an idea how internally a semaphore can be implemented. Okay. So this is the last topic in this chapter on semaphores. If you guys have any questions, you can ask them in the interactive sessions. So I strongly suggest that you guys read this chapter, because semaphores are a very important topic. As you have seen that they can be used to imitate the behavior of both locks as well as condition variables. Okay, and even we can do more things with them. So go ahead, read this chapter, and if you have any questions, ask them in a regular interactive sessions. So I will stop this video here, and thank you very much.